Hello, everyone. Today, I want to talk about optimizing large models in PyTorch. Training big neural networks efficiently requires understanding several optimization techniques that can dramatically improve performance. Let's start with the basics of the training loop. In PyTorch, each training step follows a pattern. First, the model makes predictions in a forward pass. Then, a loss function calculates the error. Next, a backward pass computes gradients using automatic differentiation. Finally, an optimizer updates the model parameters based on these gradients. This cycle repeats thousands of times during training, so optimizing each part is crucial for efficiency. PyTorch offers various optimizers including SGD, ADAM, and RMSprop. Each adjusts learning rates and updates weights differently. ADAM often works well for transformers, while SGD with momentum might be better for CNNs. The choice of optimizer significantly impacts convergence speed and final model performance. Learning rate scheduling is another key technique. Methods like step decay, cosine annealing, and cyclic learning rates help balance fast convergence with stable optimization. A well-designed learning rate schedule can prevent overfitting and improve how well your model generalizes to new data. When training large models, memory often becomes a bottleneck. Gradient accumulation helps address this by running multiple forward and backward passes before updating weights. This effectively simulates larger batch sizes without increasing memory usage. For example, accumulating gradients over 8 steps with a batch size of 4 simulates training with a batch size of 32. This technique is invaluable when working with limited GPU memory, but wanting the stability of large batch training. Mixed precision training dramatically speeds up computations by using lower precision floating point operations where possible. Modern GPUs, especially those with tensor cores, can perform FP16 operations much faster than FP32. PyTorch's automatic mixed precision, AMP, handles this seamlessly, automatically using FP16 for most operations while keeping critical computations in FP32 for stability. This not only accelerates training, but also reduces memory usage, allowing you to fit larger models or bigger batches on the same hardware. Memory efficiency extends beyond precision. Activation checkpointing is a clever technique that reduces memory by storing only some activations during the forward pass and recomputing others during backpropagation. This trades additional computation for reduced memory usage, which is often worthwhile for very deep networks. Data loading can also become a bottleneck if not optimized. Using pinned memory, multiple worker processes, and prefetching in your data loader keeps your GPU fed with data, preventing idle time between batches. When a single GPU isn't enough, scaling to multiple GPUs requires efficient parallelism. PyTorch's distributed data parallel, DDP, synchronizes gradients across GPUs while maintaining separate model copies on each device. This approach scales almost linearly with the number of GPUs for most workloads. For even larger models, fully sharded data parallel, FSDP, takes this further by distributing not just the data, but also model parameters and optimizes states across GPUs, reducing per GPU memory requirements substantially. Training stability becomes increasingly important as models grow. High learning rates can cause divergence where loss values explode, while rates that are too low lead to painfully slow convergence. A warm-up strategy gradually increases the learning rate at the beginning of training, giving the model time to settle into a good region of the parameter space before taking larger steps. This prevents the instability that often occurs with randomly initialized weights and high initial learning rates. Following warm-up, learning rate decay helps models converge efficiently by reducing step sizes over time. The one-cycle learning rate policy is particularly effective for many models. It starts with a low learning rate, increases it to a maximum value, and then decreases it again, following a specific schedule. This approach often leads to faster convergence and better generalization. Batch size selection also significantly impacts stability and performance. While larger batches give more stable gradient estimates, they sometimes lead to poorer generalization. Smaller batches introduce noise that can help escape local minima, but may slow convergence. Gradient accumulation offers an elegant solution by allowing small batches to behave like larger ones. Proper weight initialization is another critical factor for stable training. Techniques like Xavier, Glorot, and Keiming initialization set initial weights based on layer dimensions, preventing vanishing or exploding gradients early in training. These methods ensure signals can flow properly through deep networks from the start. For very deep networks, techniques like residual connections, ResNets, or dense connections, dense nets, maintain gradient flow throughout training, addressing the vanishing gradient problem structurally rather than just through initialization. While mixed precision accelerates training, it requires careful implementation to maintain numerical stability. Gradient scaling prevents underflow in low-precision computations by multiplying gradients by a large factor before backpropagation and dividing them again before the optimizer step. PyTorch's AMP handles this automatically, but understanding the mechanism helps when debugging training issues. Some layers, particularly batch normalization, often need to maintain statistics in full precision even when the rest of the model uses lower precision to ensure proper normalization. For extremely large models where even optimized single GPU training isn't feasible, model parallelism becomes necessary. Unlike data parallelism, where the same model processes different data on each GPU, model parallelism splits the model itself across devices. Pipeline parallelism divides the model by layers, with activations flowing between GPUs during forward and backward passes. Tensor parallelism splits individual layers across devices, particularly useful for massive transformer models with huge parameter matrices. These approaches allow training models that simply wouldn't fit on a single GPU. When implementing distributed training, communication efficiency becomes crucial. Operations like all-reduce for gradient synchronization can become bottlenecks if not optimized. NCCL, NVIDIA Collective Communications Library, provides highly optimized communication primitives for multi-GPU training and is PyTorch's preferred backend for distributed operations. Proper GPU topology awareness, especially in multi-node settings, ensures optimal communication paths between devices. This becomes increasingly important as the number of GPUs grows. Fully sharded data parallel, FSDP, deserves special attention for large model training. By sharding model parameters, gradients, and optimizer states across GPUs, it allows training models much larger than what would fit on a single device. Unlike basic data parallelism, FSDP only materializes the full parameters when needed, keeping memory usage low. PyTorch's implementation handles the complex communication patterns automatically, making this advanced technique accessible even without deep distributed systems knowledge. Memory profiling tools help identify opportunities for optimization. PyTorch provides built-in memory profiling capabilities that show tensor allocations and peak memory usage. External tools like Nsight Compute offer deeper insights into GPU memory patterns. By identifying memory spikes and understanding which operations consume the most memory, you can apply targeted optimizations like activation checkpointing only where needed, minimizing computational overhead while maximizing memory savings. The efficiency of your data pipeline is as important as model optimization. Slow data loading creates GPU idle time, wasting computational resources. Multiple data loader workers process and prepare batches in parallel, while prefetching loads the next batch while the current one is processing. Proper buffer sizes and worker counts depend on your specific hardware and dataset. On machines with many CPU cores but limited memory, finding the right balance prevents system thrashing while maintaining throughput. Debugging training failures becomes more challenging as models grow. Vanishing gradients manifest as stalled training progress, where loss decreases very slowly or not at all. Exploding gradients cause NaN values in loss or model parameters. PyTorch's anomaly detection helps trace such issues by tracking backward pass operations that produce abnormal values. Regular gradient norm monitoring during training helps catch problems early before they lead to complete training failure. Automated checks can alert you when gradient statistics fall outside expected ranges. Checkpointing large models requires careful consideration. Saving full model states can consume significant disk space and take substantial time. Incremental checkpointing saves only what's changed since the last checkpoint, reducing overhead. For distributed training, especially with FSDP, checkpoint formats must account for parameter sharding to correctly restore model states. PyTorch's checkpoint API integrates with various distributed training approaches, handling the complexity of saving and restoring models across multiple devices. Compilation techniques can further accelerate both training and inference. PyTorch's Torch script and more recent torch.compile transform your model into optimized code that removes Python overhead. Graph optimization identifies and eliminates redundant operations, fuses compatible operations, and applies hardware-specific optimizations. While these techniques add complexity, they can provide substantial speedups, especially for inference and when deploying models to production environments. Hyperparameter optimization becomes increasingly valuable as models grow in complexity. Techniques like learning rate finders help identify optimal starting points for training. Weight decay prevents overfitting by limiting parameter magnitudes, but finding the right strength requires experimentation. Automated approaches like population-based training adapt hyperparameters during training based on validation performance, essentially evolving the optimal hyperparameter schedule rather than using fixed values throughout training. Quantization reduces memory usage and accelerates inference by representing weights and activations with lower precision formats. While primarily an inference optimization, quantization-aware training prepares models to perform well with reduced precision. This involves simulating quantization effects during training so the model learns parameters that remain effective when quantized. PyTorch supports various quantization approaches from post-training quantization to fully quantized training for deployment to hardware with specific numerical requirements. For the absolute largest models, zero redundancy optimization, ZERO, provides a systematic approach to eliminating memory redundancy in distributed training. Stage 1 shards optimize states, Stage 2 adds gradient sharding, and Stage 3 extends to parameter sharding. Each stage progressively reduces memory requirements at the cost of increased communication. This enables training genuinely massive models across GPU clusters without requiring specialized model parallel implementations, making large-scale training more accessible. Deploying optimized models introduces additional considerations. ONNX export converts PyTorch models to a standardized format compatible with various inference engines. TorchServe provides deployment infrastructure for serving models in production. When latency matters, techniques like operator fusion, kernel tuning, and tensor layout optimization become important. The deployment pipeline must balance computational efficiency with practical considerations like versioning, monitoring, and integration with existing systems. Regular profiling throughout development identifies bottlenecks as they emerge. The PyTorch profiler analyzes both CPU and GPU operations, highlighting slow functions and excessive memory usage. External tools like NVIDIA Nsight systems provide system-wide visibility, capturing GPU utilization, memory transfers, and kernel launches. These insights guide optimization efforts, indicating whether to focus on data loading, forward pass efficiency, or communication overhead in distributed settings. Continuous integration testing prevents performance regressions as code evolves. Automated benchmarks measuring throughput, memory usage, and scaling efficiency across different hardware configurations ensure optimizations don't unexpectedly degrade performance elsewhere. Performance unit tests verify that critical operations maintain expected speed and memory characteristics. This systematic approach to performance maintenance prevents the gradual accumulation of inefficiencies that can otherwise plague complex deep learning projects. When working with extremely large models, 3D parallelism combines data, pipeline, and tensor parallelism to scale effectively across large GPU clusters. This approach assigns different combinations of model chunks and data shards to different devices, maximizing hardware utilization while minimizing communication overhead. Frameworks like Megatron LM implement these techniques specifically for transformer-based language models, enabling training of models with hundreds of billions of parameters distributed across hundreds of GPUs. For training that spans days or weeks, fault tolerance becomes essential. Elastic training allows jobs to continue despite node failures by dynamically adjusting to available resources. Gradient checkpointing combined with regular model saving enables recovery with minimal lost progress. Distributed systems introduce additional failure modes beyond just model divergence, so robust logging and monitoring help diagnose issues spanning both hardware and software domains. Automated recovery procedures minimize human intervention when problems arise. Optimization choices interact in complex ways. For example, mixed precision with large batch sizes might require different learning rates than full precision training. Gradient accumulation with activation checkpointing affects the memory computation trade-off differently than either technique alone. This interdependence means optimization requires a holistic approach, considering the entire training pipeline rather than isolated techniques. Systematic ablation studies help identify which combinations work best for your specific model and hardware. CPU offloading moves less time-critical operations from GPU to CPU, freeing GPU memory and compute resources for the most intensive parts of training. Operations like data preprocessing, certain optimizer steps, and even some layers can run on CPU while keeping critical computations on GPU. This hybrid approach maximizes the effective model size that can be trained on limited GPU resources. Tools like PyTorch's device annotations make this process relatively straightforward, automatically handling data transfers between devices. The choice of loss function significantly impacts optimization dynamics. Beyond basic cross-entropy or mean-squared error, specialized losses like focal loss for imbalance classification or perceptual losses for image generation can improve training stability and final model quality. Gradient penalty methods add regularization terms that stabilize GAN training. Understanding the mathematical properties of different loss functions helps select ones that create smoother loss landscapes and better gradient flow for your specific task. Dynamic graph construction in PyTorch provides flexibility but introduces overhead. For stable architectures where the model structure doesn't change during training, tracing or scripting the model creates a static graph that eliminates this overhead. This optimization is particularly valuable for recurrent models or those with complex control flow. The torch.compile function provides an easy way to apply these optimizations while maintaining most of the flexibility of eager execution when needed. Hardware-aware optimization tailors training to your specific GPU architecture. Different GPUs have different memory hierarchies, core counts, and specialized hardware like tensor cores. Operations that perform well on one GPU architecture might be suboptimal on another. Memory bandwidth considerations become increasingly important for large models, where data movement often limits performance more than computational capacity. Profiling on your target hardware reveals the specific bottlenecks most relevant to your setup. Normalizing inputs and intermediate activations helps maintain stable gradients throughout training. Techniques like batch normalization, layer normalization, weight normalization, and group normalization each have specific use cases where they shine. Batch normalization works well for CNNs, but becomes problematic with small batch sizes or RNNs. Layer normalization performs better for transformers. Understanding these differences helps select the right normalization strategy for your architecture, preventing many training instabilities before they occur. Gradient clipping prevents exploding gradients by scaling gradients when their norm exceeds a threshold. This simple technique significantly improves training stability for recurrent networks and very deep models. The optimal clipping threshold depends on your architecture, optimizer, and learning rate. Too aggressive clipping slows learning, while insufficient clipping fails to prevent instability. Monitoring gradient norms during training helps identify appropriate thresholds, which might need adjustment as training progresses and the loss landscape changes. Reproducibility in training requires careful seed management. Setting deterministic flags in PyTorch ensures consistent results across runs, which is invaluable for debugging and hyperparameter tuning. However, some operations have non-deterministic implementations on GPU for performance reasons. Enabling full determinism may impact training speed, but helps isolate the effects of specific optimizations from random variation. This controlled environment is particularly important when applying multiple optimizations incrementally and measuring their individual impacts. Benchmarking helps quantify optimization improvements objectively. Metrics like samples per second, time per epoch, peak memory usage, and scaling efficiency across GPUs provide concrete feedback on optimization effectiveness. When comparing techniques, controlling for factors like final model quality is essential. Faster training that produces worse models isn't truly an optimization. Standardized benchmarks like MLPerf allow comparison against known baselines, helping assess how your optimized implementation compares to state-of-the-art systems. The diminishing returns principle applies to optimization. The first few techniques you implement often provide the most significant improvements. Starting with fundamentals like proper batch size, learning rate schedules, and mixed precision training usually yields the largest gains. More advanced techniques like complex parallelism strategies matter most for truly massive models. This prioritization ensures you invest your engineering time efficiently, focusing first on optimizations with the highest return on investment for your specific training scenario.